So what we have here is a string of length L and one arc of a sine wave that matches the length of the string. That is, the arc matches the length of the string, right? Okay? And let's assume, which end are you moving? Well, we'll say that this end is the one that's being driven, okay? So that the arc is moving this way, right? Now, what's it going to look like when this point gets here? In other words, when the thing is moved the complete length of the string.
It's going to go the other way.
Well, you're going to have, the next part of the sine wave is going to be underneath, right? Because you're going to complete the sine wave. And you understand if this is being driven in simple harmonic motion that you immediately get that conclusion from what we did last time, the equations and so forth that we developed. So now you have this, but what else do you have?
You have another one on top, right?
Yeah, you have a reflected wave, and is that going to be on top? The wave reflects at this end, it changes sides.
Yeah.
So you have a reflected wave. It's moving this way, and it matches right over the top of this thing. Okay? I mean, clearly that's what's going to happen if you think about it, because last time we talked about how pulses reflect, and we saw how the pulse reflects on the other side, then it gets back, you reinforce it, because you're moving the same way again, right? And that's about as clear as mud, but you remember what we said. So this is what it's going to look like, right? Now, what's it going to look like after the source wave has moved another distance equal to the length of the string?
You're going to have a purple one on top, green one on top.
Okay, this is going to be moving this way, right?
Yeah.
And your reflected wave is going to be moving this way, right? So you're going to have this, and you're going to have this. Anything else?
You're going to have would you have a green wave on top going the other way?
Yeah, because this purple wave is going to reflect, right? So now you also have this yellow wave here. Okay? Now that's like the first three. If this is the first one down, it meshes up after another arc after it travels another length of the string, matches up with reflected wave, right? And then after traveling another length of the string, well, you get another hump of the, or arc of the purple wave, the originating wave, right? And the reflection of the reflection matches that. And the reflection of the purple wave here matches that, right? So, pretty soon what's going to happen, this is going to continue happening until this thing gets a huge amplitude, right? Except that won't happen because of energy loss. The greater the amplitude, the more you're flexing the string, and that heats up the string and you lose your energy at some point, okay? but it can build up quite a bit, okay? So this builds until the dissipative
See?
energy losses are equal to the energy of the driving force. I should really say power, but, you know, energy per unit of time and so forth, but the idea is clear enough. Okay?
And these all have the same arc length, or they all have the same arc, right?
Well, yeah, if the wave travels at constant speed and if the amplitude is small, so you don't have a lot of dispersion of the wave due to increased tension because of big amplitude,
Yeah.
okay? And of course, that increased tension will mess things up if your amplitude gets too big too, because the speeds of the waves and reflected waves will start diverging, okay? So those phenomena all limit how much amplitude you can get. In the ideal case, where you're not losing any energy, there's no limit to your amplitude. Okay? Okay, well, what I want to think about now is, well, between this state and this state, let's say halfway between this time and this time, what does it look like?